You only know that I'm recording when I tell you. The multiplexers. The multiplexers works as you can see on this figure. Looks like one input line that can go to either of the 4 possible output lines, and depending on the choice you make, then the input that we are getting at the input will be either to y0, y1, y2, or y3, and by that we achieve the objective of the multiplexing. One of the possible application of the multiplexer, think about it, would be a what? Think about a car. A car has a number of lights, isn't it? It has the parking lights. Wow, this is a car. There are some lights in front, some lights that are supposed to indicate that you are turning left, others are supposed to indicate you are turning right. It's when you are placing the brake pedal, the light. Yet, all of those are getting one input. So depending on the output that you intend, that is where you now select which output you intend to, that your power goes to. So it might go to the headlights, it might go to the parking lights, it might go to the brake pedal. So brake pedal might be one output, the parking lights might be another output, the headlights might be another output. All of them are getting one signal of either on or off. So we are saying that is the simplest example of the multiplexer. So a demultiplexer performs the reverse operation of a multiplexer. It has a single input line and several output lines. Using a switching mechanism, the input line may be connected to a required output line. Thus, a demultiplexer is also referred to as a data distributor. So, whenever I ask you in an exam, using logic functions, design a data distributor, don't get scared that I asked you something that you have never seen. An electronic circuit consisting of basic logic gates can be built to perform functions of 1 to 4 demultiplexer. So we are saying that we can use the basic logic gates to implement a demultiplexer that has one input line and how many output lines? 4. Oh, you can see the bottom part. Let me reduce the zooming then. But you are closer where I am. Now that is quite close, but full table. So we are saying that we can use our logic gates to implement the demultiplexer, and we are going to see that shortly. From this table, we can be able to derive the Boolean equations that represent for each output of the demultiplexer, where we are saying that y0 is equals to s1 bar, s0 bar, and I in. When we want these Boolean expressions are coming directly from this truth table. That is, when we want y2 to be equal to I in, it can be represented by a Boolean expression that says s1 is going to be 1 and s0 is going to be bar or to be 0. Okay? Can see people struggling to see. Let me see if I can see from the back. Then you can also see. Or can I project from top? So we are saying that we can be able to relate that this equation is coming from this truth table. It is simply saying that y0 is equals to s1 bar, s0 bar, and I in. Etc. So if I asked you to now from those 4 Boolean expressions, you can be able to implement the 1 to 4 line demultiplexer, isn't it? Because you know when you find a bar, the one that professor uses as apostrophe, that is an inverted S1, isn't it? When you find this S1, this is of course not that. S1 bar comes outside there. Then you need to add it with S0. So you have S0 there, comes that point. And you have I in, comes as I in there. So these 3 are simply ANDed, isn't it? Or not noted. So when they come outside there, this is your y0, isn't it? Oh, y0. This is y1, right? Oh, I cancelled. But I know you have seen. So this becomes this how we implement this, and as you can see, we have y1 simply taking the inverted. Let's see. Takes S0 as without inversion. The S1 is inverted and is the one that comes at this point. And the other thing that we remember we included is the chip enable pin and our input line. Then our input line may be a 0 or maybe a 1. So depending on what your input is, your output is going to be dependent on what you have selected down there and what the I in is, isn't it? So having said that, then we need to talk about the gate level implementation of this 1 to not gate level, the symbolic representation of that 1 to 4 line demultiplexer. And all we are saying is that everything gets inside that box. So our input is I in there. The chip enable is down there as a low input. What do you call it? Active low input. The 2 select lines are down there, and the outputs are 4. So that is what we have on that diagram on the right. Okay. So that is the symbolic representation of 1 to 4. It's supposed to be written like that one. 1 to 4 line Dmucs. So you can just use the short form of the multiplexer to call it Dmucs. And that is it we need to know about the multiplexers, except that you may be required to implement a higher level or a larger capacity demultiplexer using a lower level demultiplexers like we are doing now. in this figure, we are implementing, the gentleman is dozing when he is looking clearly in my eyes. We are implementing a 1 to 8 demultiplexer using a 1 to 4, just like we did with multiplexers. So we are saying that a larger capacity demultiplexer can be implemented from lower order demultiplexers. For example, a 1 to 8 demultiplexer can be built with 1 to 4 demultiplexers, as you can see on figure 1 2. When S2 is 0, now this is what we need to do like we did the other time. We just need to know I can use a diagram on a different page. Will allow you to see what I'm doing. Telling you I'm moving digital. You will not believe it until you see. This is loading. This is my digital whiteboard. Oh, my iPad is quite slow. Is that you want to turn this one on using the S2, just like we used the chip enable pin to turn one of the multiplexers on when the other one is off. So what we know is that if this is my chip enable pin CE and this is 1/4 Dmucs, my Y0, Y1, Y2 and Y3 are going to be, if this is a 0, we say that when our chip enable pin is 0, the chip itself is going to be active or inactive. It's going to be active, and therefore this becomes our I in. Therefore, when this is 0, they are going to be displayed correctly. So if we want now the other demultiplexer to display Y5 or Y4 to Y7, that is the point. Then this needs to go S0, S2 will be 1 at that point. For, of course, that means, let me show you what that means. To represent Y4, this is represented by 1 0 0. That is for S2, S1 and S0. Oh, I can't see that. That is what I'm saying. The most significant bit is S2, the second significant bit is S1, and the least significant bit is S0. So in that case, we are saying that Y4, Y5, all the way to Y7 are going to have S2 as 1. Y7 has Y111. So what are we saying? That this one can be used to turn on the second demultiplexer. So that only, and at that point, only these 3 or these 4 are going to be displayed. So in that case, what does that mean? It means that for us to use this second demultiplexer that requires a 0, we need to put S0, S2 through an inverter so that it becomes a 0 when, or the other hand, when we know it is supposed to be a 1. That makes sense? I need one person who sees that it makes sense. You might have written very many things till you got lost. But this is how we are implementing this. So what I was trying to explain in so many words is this. that S2 right here will go to chip in number pin directly, so that when it is 0, it activates the first demultiplexer. When it is at this point between Y0 and Y3, we have seen that S2 is going to be 0 from the basic representation of binary numbers. And therefore, when it is 0, only this demultiplexer is going to be active. So that 0 that was there at S2 gets inverted and comes out of this inverter as 1. And at that point, when a demultiplexer receives a 1 in its chip enable pin, what happens? It is active or inactive? It is inactive. Therefore, none of these are going to be displayed. Okay? So we are saying that S2 is the one that is going to be inverted to deactivate the lower demultiplexer that represents the higher outputs, whereas this one receives a direct input. So when you want to output to a 5, we know 5 is represented as 1, 0, 1, and therefore this one comes inside the chip enable pin of the first demultiplexer, and if it gets there, this becomes deactivated, and therefore none of these are going to be output. Okay? So much to do with the multiplexers. That is the head. So if I ask you now to implement, let's try to see if you can get what we usually do. Implement a 1 by 16 Dmucs using 1 by 8 Dmucs. Just apply what we have learned. It is quite straightforward. Oh yeah. A decoder has several inputs and output lines. The function of the circuit is to detect a specified combination or code formed by the inputs. For n input lines, a decoder circuit may have up to 2 to the power n. Oh, this is 2 to the power n output lines. So if you have say a decoder, okay, takes this form. If you have 3 inputs, what do we expect the number of outputs to be? 8. So we are going to have 8 outputs. With the decoder, we don't have what? What is somebody here? Select lines. We don't have select lines. So we will start with a binary decoder. And a binary decoder, or a decoder with a ratio of input to output lines given by n to the power n, as I have said, is termed as a binary decoder. Let us consider the gate level implementation of 2-line to 4-line decoder. So it means that if you have 2 input lines, how many output lines do we have? 4. So you want to implement, these are 2 inputs, A and B, and the outputs are going to be Y0, Y1, Y2, and Y3. Let us see how we can do that at the gate level, because we said we want to understand how a computer would work. And the computer is the one that is formed by many gates at a higher level. The inputs are the logic variables A and B. 4 combinations or codes can be formed from A and B. These are the ones that are indicated there, and these are the ones that you always say that when you have A and B, you have how many possible combinations? You have 0, 0, 0, 1, 1, 0, and 1, 1. So these are the 4 possible combinations, and if you write them in this form, you would have A bar, B bar, A bar, B, A B bar, and A B. The decoder is thus a generator of all the possible minterms. That is now the beauty of working with a decoder. it generates all the possible minterms. And you remember, if you have a 3 variable Boolean expression, how many minterms do you have? You have A, B, C. These are 3 variable expression. So you have how many minterms that may be represented? 8. Very good. So we are saying that a decoder generates all the possible minterms depending on the number of inputs. So these inputs that we are saying, A, B, C, are the inputs that go into a decoder. A comparison of figure 413 and 411 shows that a 2-input decoder is identical to a 1 to 4 line demultiplexer. We're comparing figure 413 and figure 411. This is figure 413. Look at figure 411 right here. You observe that the implementation at the gate level is the same. Why is that? There is some slight difference. Yeah? And so if you say, then someone has just answered, if you say A is equals to S1 and B is equals to S0, is there any other difference? Very slight one that you may not necessarily see. What we don't have in this circuit is the what? Is the input line that went everywhere, isn't it? That is the only thing that we don't have. Otherwise, this is the same way we are implementing a demultiplexer. So what we are saying is that it combines the functions of a multiplexer with a multiplexer, such that it will have many possible inputs and many possible outputs. And the symbolic representation of 2 to 4 demultiplexer is the one that I have highlighted. My mic went. Should be very close to me. That receives my audio pretty well. I'll get a better mic with time. Okay, so having said that, we want now to use the demultiplexer. So I wouldn't necessarily go back into implementing the gate level implementation of a demultiplexer, because we have seen how it is done. Therefore, we skip that part. We want now to go to practice. We want to practice what we have learned. Then the question is asking, implement the following functions using a decoder and some external logic gates. This is quite straightforward, because we said if I can draw I don't need to draw a demultiplexer here. I just want to illustrate one. There is a demultiplexer there. The input 0 or the output 0, it is equivalent to minterm 0, minterm 1, minterm 2, 3, 4, 5, 6, and 7. So if you are to express minterm 7 in form of variables A, B, and C, it would be equals to what? Minterm 7 is equivalent to 1, 1, 1 is equivalent to A, B, and minterm 6 is equivalent to 1, 0, 1, 1, 0, and this is equivalent to A, B, C bar. And that's the story ends there, isn't it? So if you want now to implement a function of this form, if you wanted to implement a function of this form, we would simply draw a demultiplexer here, and you say this is minterm what? When you find you have A bar, B bar, C is don't care. So you normally write it twice, isn't it? One with a bar and the other one without a. So this becomes min term what? Min term 1. This becomes min term 0. Therefore, at where we have 0 here, we say that is these two are represented by that. Then the other one, this one is what? Is min term what? A B bar C. That is a 5, isn't it? So a 5 becomes one min term, and the last one is B bar or B C bar. That is a B C bar, A B C bar bar. So this becomes min term what? 6. This is min term 2. So you say 2 is there and 6 is there. All of the ones that we have generated, we take them through an OR, because this is as SOP. F1 is SOP, so you take them through an OR. And that becomes F1. That is the end of the story. That is how you implement function F1 using a decoder. If you are to implement function F2, you do a similar procedure. As long as you are able to identify which min term is represented by the variables, then you are very set. Sawa sawa? Very good. That is gone. And the solution is right there. So this is the solution if you want to look at it in more detail. I don't want to look at the BCD to 7 segment. That you can look at it in your own leisure as a computer scientist and IT experts. So you can look at that. We jump to encoders. Today we are going marathon, if you have not noticed. We want to say now that encoders perform the reverse operation of a decoder. It gives a unique code for each input line that is activated. Okay, that is a very good description. Yeah. Now I've remembered where we deal with encoders. We normally deal with the priority encoders. But before we go to the priority encoders, we just discuss very briefly what the encoders do. Consider an input line, let's say, and this is our encoder, A and C. It has 4 input lines, 1, 2, 3, 4, that we are labeling A, B, C, and D. This decoder will have how many possible output lines? 2 to the power, which is equals to so we might have 16 possible inputs. So if we activate A, wait a minute, I will do that statement. The correct form of an encoder is this one. Let's say we have 9 input lines. I'm looking at figure 418. Assume you have 9 input lines. In this case, since we have said it works in reverse of a decoder, then the number of input lines are going to be n, and there's the output. The input is here. Input is going to be 2 to the power. So if you have 8 inputs, then n is equals to what? N is going to be 3. So assume you don't have this D there. You have only A, B, C, and you don't have this 9. Then we have agreed according to this rule of 2 to the power n is equals to n. Inputs and outputs. Are we agreeing on there? Let me not hear the mamas. So once we agreed there, then we are saying that when you activate I0, a code for I0 which is 0, 0, 0 is displayed at the outputs. Are you getting? If I activate I0, that is I turn it on, it has only 2 possible inputs or states, as an on or an off. That gentleman is with us, or he is on his own business. Let me see where he is. And we are saying that I0 or I0 has 2 possible states, on or. So when you turn I0 on, the code for I0, which is midterm 0, is 0, 0, 0. So you will get the outputs as 0, 0, 0. Now tell me something. If you turn on I7, what will be the output at A, B, C? That is straightforward. Very good. So we are together. That is what an encoder does. It encodes which line you have activated. So if you activate a 5, you get a 1, you get 101, etc. So having said that, we can move forward and now jump directly to what we call decimal to BCD priority encoder. And before we do that, let's go back here. Consider a scenario. Consider a scenario where you have activated I0 and I1 at the same time. What code do we get here? We have 0, 0 and we want to combine both of them. What gets outputted? It is going to be a confused situation. So this is not an ideal encoder. We want to prioritize the input line that gets at the output. Okay? So that is why we are calling what? We are saying the one that we want to work with is a priority. Fantastic. I can see we are moving together. We should always have such classes that are cooperative. I don't know what happens to you sometimes when you are not in a mood. So does it? Let me pause before I say what I want. So we are talking about decimal to BCD encoder. You remember something that we said about BCD? We said BCD code has how many? It represents 0, 2, 0, 1, 2, all the way to? Where? BCD code has how many possible outputs? 0, 1, 2, 3. Tell me when to stop. I'm waiting for a stop. I stop. Go on, huh? I go on. Huh? You are disappointing. I stop at that point. It represents 0 to 9. You remember something we say that BCD number only has 4 possible binary values. 0, 0, 0, 0. And if I told you to represent, like if I told you that 27 is a BCD code, to convert it to pure binary, oh no, to convert it to pure binary, you simply need to do divisions. 27 divided by 2, blah blah blah. You get some number somewhere, 1 1, blah blah blah. But if I told you to convert this 27 to a BCD code, you would convert only 2 becomes 0 0 1, and 7 would become 1 1 or 0 1, 3 zeros, isn't it? Now that is what you want to apply here. So you want to have a decimal number that ranges from 9 to 0 to be represented by a BCD code, which has 4 possible binary numbers. Okay? So we know that a 9 is represented by a BCD code as 1 0 0, isn't it? And an 8 is represented by a etc. So when we want to activate line 9, we want 1009 1001 to be output at this output there. So that means we are prioritizing in a way. What we normally prioritize when we talk about the priority encoder is the higher significant number. If I turned on 6 and 9, which one would be my priority? 9. If I placed 5 and 7, my priority is, that is what means that if I place both of them at the same time, the code that will be displayed is that one of the higher number. And now if you look at this truth table, you will notice that the BCD code that is output is the one that is higher. So if we have all of them are inactive, we display 000, but we have a status bit at the output that says that when none of them is activated, we say that status is 0. Otherwise, at least one is activated, and the status bit remains 1. So when we want to output I0, this becomes the priority. The others are not prioritized, and that the BCD code output becomes 000. If we have 1 and 0, now that is where things start getting interesting. If you have 1 and 0 activated at the same time, you treat 0 as a don't care, and you only prioritize for 1. If you have 2 activated, same as 1 and 0, you ignore this as X and you ignore that as X. We know in digital logic or digital electronics, when we have an X, we mean a what? A don't care condition. You don't care what that value is. But notice that we are caring when we are saying these are zeros. Zeros are important, are significant. But don't cares are just ignored. Okay? So in this case, we are saying that we may have I1 and I0. Let me delete that. Say that in this case we have 2 possible states. That 1 is active and 0 is active. But we ignore the 0 and we take the 1. And therefore what is going to be displayed is a BCD code for 1. Now finally, consider this scenario, the last but one row. Consider this one. That row says that if you have all these possible activated, that is I8, I7, all the way to I0, the only one that you will not ignore is the for which one? I8. Yes, very good. We are making huge strides as far as encoders are concerned. So let us go to what is now complex. Should prepare you for this. Tell you that this is not as easy. This is not a walk in the park. what we want to do is to write the Boolean expression for these conditions. We want to write the Boolean expression. That is the one I said that this is not a walk in the park. But we are braving ourselves to go through the park. So let's start here. From the truth table, it can be deduced that the input line D is high under the input line conditions as follows. I'm tired. Let me take a break of 2 minutes. We are at a point where we want to do the Boolean expressions for the outputs B, C, D or A, B, C, D, and we are saying we are looking at D first. Look at this. When you want to write the Boolean expression for the output D, you look at the times when it is what? When it is 1. You can tell me when the D is 1. When is D1? When I1 is true, isn't it? When else? I3 is true. I3 is true and my eyes. I5. When else? I7 and I9. That is the first thing that we have identified. But we need to differentiate between when we have at some don't cares and when we what? When we don't. So you are saying that D is 1 if I9 my eye has just started paining, seriously. I have to pause. So we are saying we need to differentiate between when we have a 1 with excess on the right and when you have a 1 with excess on the are we following? We are comparing these two possibles of having a 1. Let's not look at that, but let's start compare only for D. Consider that scenario. My eye. They reduced our semester by 1 week. Did you notice? Our semester is supposed to be 14 weeks. So in the midst of you guys going for elections, coming back, going for the second elections and coming back, we lost 1 week. So we have 13 weeks. Now the one of the 13, we missed the first 2. The one that we never attended. So we are left with 11. Of these 11, I went away 1. We have 10 remaining. Of these 10, we have done a cut. We are left with. Now of these 9, what happened? One time we were kicked out of our class by a lady. And so we are left with 8. We have met how many times? About 5. About 5. This is the 5th time. We are most likely meeting, or 6. So of the about 6th time. So of these 8 remaining, we are remaining with 2. You see, we have not spent much time. We have not wasted much time. So only that circumstances have come in. Elections are later kicking us out. So what we need is to catch up what we must cover. That is why I said I need some few people to attend a class. We discuss what we are discussing, then the others can view the recording. So what was discussed is quite important here, because now after what we have done, what I was trying to write is now represented there. That is all the possible conditions that we started with I9 alone, then I7 with I8 bar, I5 with I6 and I8 bar, I3 with I4, I6 and I8 bar, and lastly I1 with 2, 4, 6 and 8 bars. So that is the logic expression of D. Now if you are to write the logic expression for C, for D, and for B and A, you will get to this point, and that is what you need to do. That is logic level implementation of a what? Priority. So if I ask you to do that, don't get scared. They just require some work to do, but it is doable. Very good. We move on. So there's an example there, you can look at it. That is not for us to do. We jump now to the 2-bit comparator. Do I want to do this? Yes, we want. We don't have an option. We compare 2 bits when we are talking about 2-bit comparator. And if we have A1 and A0 and compared with B1 and B0. So if we notice that A1 is bigger than B1, then we say that the output Y1 is what? We want to let us just state it correctly so that we don't have to repeat these things. The 2-bit comparator has 3 outputs. And how many inputs? 4 inputs. The first 2 inputs represent one series of 2 bits. The other 2 represent the other series that you want to compare with the first series. From what you get from this comparison, you activate these outputs as follows. That if A series is equals to B series, that is both of them are 0, 0 or 1, 1 or 0, 1, 0, 1 or 1, 0, 1, 0, then you do the following. The following is here. The following is this one. That Y1 is true if A is equals to B. Okay? Y2 is true if A is less than B. And Y3 is true if A is bigger than B. So we are simply comparing. So what are we saying? That only one of them should be on at a given instant. Now compare this and tell me that is true. Only one of them is on at a given instant. That when all of them are 0, we activate the first one, isn't it? When A series is less than B series, we activate the Y2. If this is still the case, B series is still bigger than that one, then we have A series is bigger than B series, and therefore we activate the last one, and the story goes like that until you have that truth table of 2-bit magnitude comparator. You know, we have barely made 1 hour since we started teaching. So you group, we are saying that we are feeding the kernel map from the output of y1, depending on what the inputs were, you have filled them in the first kernel map for y1, and then to simplify, like this table cannot be simplified any further. Are you seeing that? Because there are no groups of 8, there are no groups of 16, there are no groups of 4, neither are there groups of how many? 2. I doubt some people are still with us, but nevertheless, the interest of majority is supersedes the interest of an individual. So if someone decides by their own decision that they don't want to concentrate, why should we push them to concentrate? Hope I'm not recorded. But the second kernel map, there are some possible groupings. So once you group, you notice that you get A1 bar, B1, etc. So from those ones, you can say that Y1 is equals to, okay, I don't want to do for Y1, I want to do for Y2. From this, we can see that Y2 is equals to, this group is A1 bar, B1, or, so we have done with that group, or which other group? This other group of A1 bar, A0 bar, and B0 plus this other group of, this other group. That becomes our Y2. I believe it is listed down there. So of course you can see that Y2 is equals to that, Y3 is equal to that, and Y1 is equal to that. That is gate, that will now allow us to do gate level implementation of what? Two-bit comparator. I can see you are very attentive. Today is a very good day, but we were just had swearing in yesterday, so that might be the reason why. What we are learning with others is that we are asking ourselves, how does a computer take a 1 plus 1 and it knows that the answer is 2? You know, a computer is not a person, doesn't know how these things happen. So we are going inside the computer, because we are going to become computer experts and ICT, or computer scientists and IT professionals. So you must be able to understand how this addition happens, how comparison that we just looked at happens in a computer, because everything in computer is in ones and sometimes I try to be funny, but I'm not funny. So I would rather get used to it. Addition. So we have two variables. We start with half adder. Half adder, you'll notice how stupid a computer is. Half adder does addition, and if it goes, say, 5 plus 6, it will say that is a 1. It will not carry the one that ideally someone should carry. So if you are doing A is 5 and B is 5, or is 5 again, it will only get the one answer correct. Oh, wait a minute, that is a mistake. Let me tell you what that means. Let me repeat the story. It does know what to carry. What it doesn't do is if there was some carry brought forward. So like if we are adding 27 plus 34. If you are adding this one, it will add this one, gives you a carry carry 1. This carry 1 will not go anywhere. It will only know that there was a 5 there. That is incorrect answer. So we are starting with half adder. Then we'll do a full adder that knows that there was a 1 carried and adds to this one. So let's see how that happens. A basic adder can be implemented with an XOR gate. Let us consider this. Forget about that story. Let us just know that we have two variables A and B, and we have sum and carry bit. For those who cannot see, this is sum S and this is carry bit. This is one variable A, one variable B. Consider a situation where we have both of them are 0, 0. What happens? The sum will be and the carry will be okay, very good. Consider now a situation where we are jumping one line and go to the next one. Consider a situation where A is 1 and B is 0. When you add them, 1 plus 0 is equals to carry. So it will correctly record that the answer is sum is 1 and carry is 0. Consider now another situation where we are adding 1 plus 1. The answer is supposed to be 0 carry. So this is still do fine. This is carry comes there and sum is. That is how a half adder works. How do you implement half adder using basic gates? This is how you do it. You just observe when do you have ones. We have a 1 for S. S is 1 when is equals to A bar B or this other one A B. That is why you are seeing this is our S. A B bar or A bar B. And this is what we call an XOR operation. Do you remember the XOR? Yeah, this is an XOR operation. It is saying that they are exclusively OR. Neither of them are the same. And then if you are now to do the gate level implementation of S, you see it is straightforward. This is XOR of A and B. And from what we have not done, we have seen that when C equals to what? When is C equals to 1? Only when both of them are. And therefore we say that C is equals to A, B. These things are simple. So you see that this is an XOR operation and this is an AND operation. That is gate level implementation of half what? Half AND. And this is the symbolic representation of yes. We want to maintain the good discipline that we have adopted. Full adder. Now this full adder now add something in addition to A and B. It remembers that there is a possibility of having some carry in bit. Okay? Aye. You're getting tired? Don't get tired so quickly. So we are saying that in addition to variables A and B, we are considering a possibility where we had carried some other bit. Now this is the situation. You have A plus we are saying this is the best case scenario where we would see how that would happen. We are saying that we have 27 plus 34. This is A1, B1, and this is not that one. A1 is A0, is B1, B0. Huh? So if you are adding, we start with A0, B0. So we say 7 plus 4 is equals to 11, isn't it? Our sum is 1 carry. This carry 1, if you don't bring it there, if you only do A1 plus B1, you not get the correct answer. So we are saying that whenever you are doing the addition, you put an additional possible carry that might have been carried during the previous operation.